Welcome to Talk Sensors.
Good to be here.
You know, when we look back at the history of technology, and I mean specifically the history of AI, there are these really distinct eras.
Yeah, you have the AI winters, the connectionist revival.
Exactly. There's the deep learning boom, and now what everyone's calling the LLM revolution. But inside those big eras, there are these specific years that just feel like pivot points.
The moments where the whole field just turns a corner.
Right. And today, we are going back to one of those hinges. We are dialing the clock all the way back to 2015.
Which is ancient history in AI years.
It really is. And to someone on the outside, 2015 might just seem like another year. But if you were in the lab, if you were, submitting to ICML or NeurIPS back then, it was a time of absolute, chaos.
It was chaos. The best kind of chaos. We had just started to figure out how to train really deep networks reliably. ResNets were right around the corner.
And Jan's generative adversarial networks had just exploded onto the scene a year earlier.
Right, so there was all this energy. But there was this one corner of the room, you could call it the probabilistic corner, that was really struggling.
How so?
Well, we had these incredible new models, like variational autoencoders, or VAEs, which promised to combine deep learning with principled probability theory. It was this beautiful dream.
But there was a problem. A really big, glaring mathematical crack in the foundation.
A variational gap.
Variational gap. It sounds pretty ominous.
It was ominous because it was the difference between what our models could theoretically do and what we were actually forcing them to do in practice.
So we were crippling them from the start.
Totally. We were building these massive, high-capacity neural networks, Ferraris of computation, and we were putting square wheels on them.
And today, we're doing a deep dive into the paper that finally gave us round wheels. We are breaking down Variational Inference with Normalizing Flows by Danilo Jimenez-Razende and Shakir Mahamed from Google DeepMind.
This paper is a true classic. It's one of those papers that gets cited constantly, but I think very few people actually sit down and work through the derivation of why it works.
Which is exactly why we're here. The mission today is to demystify this whole thing. We're going to explain how you can take a simple, boring probability distribution like a blob of noise and twist it and stretch it and fold it into a really complex representation of reality.
And crucially, without breaking the laws of mathematics.
Or waiting a million years for the computer to finish the calculation.
That part's important too.
Exactly. So before we get into the how, the flows, the Jacobians, the determinants, let's really set the stage with the why. What was the specific pain point that Razende and Mahamed were trying to solve in 2015?
Okay, so to understand the pain, you have to understand the context of amortized inference.
Right, which was a relatively new idea at the time.
Very new. Just a year prior, in 2014, Kingma and Welling had published the original VAE paper. And that really changed everything because it finally allowed us to scale variational inference to big data sets.
Can you just quickly remind us what that means? Before amortized inference, what did you have to do?
Before that, if you wanted to infer the hidden variables, the latent state of your data, you had to run a massive optimization loop for every single data point, every single image you saw.
So for a data set like ImageNet, that's just impossible.
Completely impossible. Amortized inference changed the game by saying, let's not solve this problem from scratch every time. Let's just train a neural network, an inference network, to solve it for us.
So you show the network an image of a cat, and it instantly spits out a guess for the latent variables. Pointy ears, whiskers, fluffy.
Ideally, yes. That's the dream. But here is where the square wheels come in. To make all the math tractable, and specifically to make the calculation of the Kale divergence term in the loss function possible. Everyone was making this massive simplifying assumption.
The mean field approximation.
The mean field approximation.
Okay, that's a term borrowed from physics, I think. In plain English, what are we assuming about the world when we use a mean field approximation?
We're assuming total independence. We're assuming that all the latent variables that describe the data have absolutely nothing to do with each other. They're all just independent little knobs.
Let's ground that with an example. If I'm modeling a human face.
Okay, a great example. If you're modeling a face using a mean field Gaussian, you are mathematically stating that the probability of the left eye being open is completely statistically independent of the probability of the right eye being open.
Which is obviously ridiculous. If I blink with both eyes. They are highly, highly correlated.
Exactly. Or, think of a robot arm. The position of the hand is strictly dependent on the angle of the elbow and the shoulder. You can't just move them independently.
But the mean field assumption forces the model to treat them as if you could.
Yes. It breaks the very structure of the object you're trying to model. You are effectively telling the model, hey, just assume the world is made of a bag of unconnected parts.
And what does that do to the model's performance? What's the statistical consequence of that bad assumption?
Well, it leads to this classic problem of underestimation of variance, because the model is forced to fit a really simple spherical shape, the Gaussian, into what might be a complex, maybe banana-shaped true distribution.
The banana being the true?
The banana is the truth. The only thing the model can do is hide inside the thickest part of the banana. It just finds the center of mass and puts a blob there.
So it huddles in the center and just completely ignores the tails, the curvy parts of the banana?
Precisely. It becomes overconfident. It thinks it knows the answer with very high certainty, but it's actually ignoring vast swaths of possible solutions because its square wheels just can't drive into those complex corners of the probability space.
So in 2015, you basically had two choices on the menu.
Yep.
You could do variational inference or METZIX, which was fast thanks to amortization, but wrong because of this mean field assumption.
Fast but sloppy.
Or you could do Markov chain Monte Carlo, MCMC.
The gold standard. MCMC is asymptotically exact. If you run it long enough, it will find the true distribution. It will map out the entire banana perfectly, every curve.
But there's always a but.
But long enough might be the age of the universe. It's incredibly computationally heavy. You generally can't put a full MCMC chain inside the training loop of a deep neural network that needs to process, thousands of images per second.
So the whole field was stuck in this terrible trade-off, fast and sloppy or slow and precise.
Exactly.
And this paper, Variational Inference with Normalizing Flows, steps into that gap and says, why not both?
Or at least it says, let's make the fast version much, much less sloppy.
So let's get into the solution. Normalizing flows. I have to say, I love the imagery of this term. It sounds so fluid, so dynamic.
It is fluid. And the core intuition is really geometric, which I think makes it easier to grasp.
Okay.
So imagine you have a probability distribution. And in the paper, they start with a really simple one, usually a standard spherical Gaussian, zero mean unit variance. The simplest blob you can imagine.
Okay, I'm visualizing a blob of clay, a perfect sphere, sitting there on a pottery wheel.
That is your base distribution. It's simple. You know the math for it inside and out. You know exactly how much clay is there, which is to say the probability integrates to 1.
Got it.
Now, your goal is to turn this sphere into a much more complex object, the true posterior. Maybe the true distribution looks like a donut or a crescent moon or two completely separate islands of probability.
So a normalizing flow is basically a sequence of transformations, maybe let's call them hand movements, that mold that clay.
Yes, that's exactly it. You apply a function, let's call it 50 other, then you apply another function, 52, then 53, and so on. You write it as zk du Bélier.co.
So you're stretching the clay, you're squashing it, you're twisting it.
Right. But there are very strict rules to this pottery class. You can't just do whatever you want to the clay.
Okay, what are the rules?
The most important rule is invertibility. You cannot break the clay, you cannot add new clay, and you cannot remove clay.
So the total amount of clay always has to stay the same.
Yes, and crucially, you cannot merge two different pieces of clay together or tear a hole in it.
Mathematically, that means the function has to be a bijection, a perfect one-to-one mapping.
Exactly. If I film you sculpting the clay from the sphere into the donut, I must be able to play that film backward and see the donut turn perfectly back into the original sphere.
Why is this backward play, this invertibility so critical? Why can't I just, mash the clay into the shape I want?
Because we're dealing with probability density. We need to be able to calculate the likelihood of any given data point.
Yeah.
If you just mash things together, say you take two different points in the input space and map them to the same point in the output space, you've destroyed information.
Oh.
Really?
You no longer know where that density came from. To train the model, to calculate the loss function, we need to be able to track exactly how the density changes at every single step of the process.
And that tracking process brings us to the engine room of this paper. The one formula that makes it all possible.
The change of variables formula.
Equation 5 in the paper. This equation introduces a term that I think scares a lot of people away.
Another one.
The Jacobian determinant.
Laughs. It does sound intimidating. It sounds like something from a spy novel. The team needs to recover the Jacobian identity.
Exactly. But conceptually, if we just stick to our clay analogy, it's actually really intuitive. So let's unpack it.
Okay, so the Jacobian matrix itself is just a big grid of all the partial derivatives of your function. It tells you the slope of the function in every possible direction.
So it describes how the space is being warped right at that one point.
Precisely. But the determinant of that matrix, that's the magic number. The determinant collapses that whole grid of numbers down to a single value that tells you the local volume expansion factor.
Okay, volume expansion factor. So if I take my blob of clay and I stretch a little section of it to be, say, twice as long.
You have expanded the volume of that section. The points are spreading out.
And if the points spread out, the density of the clay in that spot must go down, right?
Exactly. It's just conservation of mass. If volume goes up, density must go down proportionally.
It's like pulling on a piece of taffy. It gets thinner.
Perfect. The Jacobian determinant measures exactly how much the volume changed. So to find the new probability density, you take the old probability density and you divide it by this determinant.
Or multiply by the inverse of the determinant, which is what they do in the paper.
Right. And if you squash the clay, compress the volume, the determinant is less than 1, and the density shoots up, the determinant allows us to track these fluctuations perfectly.
So in theory, this solves everything. We take a simple Gaussian, we apply a bunch of these invertible functions, we track all the volume changes using the Jacobian determinant, and voila, we can model any complex shape we want.
In theory, yes. It's beautiful. But in practice, there was a catch. A big, expensive computational catch.
The bottleneck.
The bottleneck. Calculating the determinant of a generic matrix is hard. If you have a matrix of size $$ times d, where the dollars is the number of dimensions in your latent space computing, the determinant has a complexity of order $cubed.
Sure.
Yes, cubic complexity.
Let's put that in real numbers, because cubic complexity sounds abstract until you actually have to pay the cloud computing bill.
Right. Well, if your latent space is small, say 10 dimensions, then 10333 is 1,000 operations. Trivial for a modern GPU.
But in deep learning, we don't want 10 dimensions. We want rich representations. We might have a latent space of 500 or 1,000 dimensions.
Right. So let's take 1,000. 1,333 is
1 billion.
1 billion operations.
Just to calculate the probability of one sample.
A single sample. And you need to do this for a whole batch of, say, 128 samples, thousands of times per training epoch for hundreds of epochs.
So your training time goes from let's grab a coffee to let's wait for the heat death of the universe.
Exactly. This is the Jacobian bottleneck. And this is why normalizing flows didn't really take off earlier, even though the math of the change of variables formula has been known for centuries. It was just computationally intractable.
And this is the hero moment for Razende and Mahamed. They didn't just write a paper saying, hey, flows are a cool idea. They wrote a paper saying, here's a specific way to build flows where you don't have to do the billion operations.
Precisely. The core innovation of this paper, the practical magic, is the proposal of specific families of transformations where the determinant can be computed in linear time.
So OD.
We go from 1 billion operations down to 1,000.
That is the difference between impossible and let's run this experiment this afternoon.
That's the difference.
Okay, so let's talk about these magic transformations. They proposed two main ones in the paper, planar flows and radial flows. I really want to visualize these. Let's start with planar flows.
A planar flow is defined by a hyperplane. So imagine a flat sheet, like a piece of paper, cutting through your high-dimensional space.
Okay.
The transformation takes every point in that space and it shifts it. But the amount it shifts depends on how far the point is from that sheet. And it only shifts it in one specific direction.
It reminds me of, like, shearing a deck of cards. You push the top of the deck, and the top cards slide more than the bottom cards.
That is a great analogy. Or slicing through a block of gelatin and sliding the top half relative to the bottom half. It expands or contracts space perpendicular to that slice.
And the formula for this is y/z plus u delay v dot h wtz plus b.
Right. And the reason this is so fast to compute is because mathematically this transformation corresponds to a rank 1 update to the identity matrix.
Okay, that's a bit of linear algebra jargon. What does it mean for us?
It means there's a mathematical shortcut. There's something called the matrix determinant lemma that lets you compute the determinant of this very specific type of matrix using just a simple dot product. No heavy matrix decomposition required.
It's like finding a secret back door into the math that avoids the billion operation long hallway.
That's a great way to put it. It's a computational hack based on a clever mathematical identity.
Genius. Okay, so what about the second one, radial flows?
Radial flows are, well, exactly what they sound like. Instead of being organized around a flat sheet, they're organized around a single reference point, a center.
So the transformation is either expanding away from that point or contracting towards it.
Yep, like an explosion or an implosion centered at a specific point in space.
I can see how that would be useful.
It's incredibly useful. You can use it to push probability density away from a center, creating a hollow shell, or you can use it to suck density into a center, creating a very sharp peaked mode in your distribution.
This seems perfect for multimodal distributions. If my data looks like a donut shape, radial flow seems like the perfect tool for carving out the hole in the middle.
It is. And by chaining these simple operations together, a planar flow to slice the clay, then a radial flow to expand a part of it, then another planar flow to shear it, you can start to sculpt that initial Gaussian clay into incredibly intricate shapes.
So we have the clay, which is our base distribution. We have the hand movements, which are the planar and radial flows. And we have the shortcut, the linear time determinant calculation. Now we have to actually train this thing.
Right. We have to fit this whole apparatus into the standard variational inference framework.
Okay, so normally in CLAG, we're trying to maximize the evidence lower bound. But since we are actively warping the space, I'm guessing the ELBO must look a little different.
It does. They derive a modified objective function, it's equation 15 in the paper, which they call the flow-based free energy bound.
That sounds like a weapon from a sci-fi movie. Captain, we need to charge the free energy bound.
It's a powerful equation. It looks almost identical to the standard variational bound, but with one crucial addition.
Let me guess. It involves the determinant.
It involves the log of the determinant. It has a new term, which is the sum of the log absolute values of the Jacobian determinants from every step in the flow.
Okay, so we're adding up all the log volume changes. Why? What does this term do?
It acts as a kind of regularizer. You can think of it as a tax you have to pay for warping the space.
It's a tax.
Yeah. Think about it. If the model's only goal is to maximize the likelihood of the data, the easiest cheat would be to just squash all the probability mass into an infinitely small, infinitely dense point right on top of each data point.
Right. You get infinite density. Perfect score on the likelihood term.
But that's a completely degenerate solution. It hasn't learned a distribution, it's just memorized the data. We want a distribution that generalizes.
Okay.
The log determinant term prevents this. It penalizes the model for squashing the space too much. If the determinant is very small, which means lots of squashing, the log determinant becomes a large negative number, which hurts your overall score.
So it forces a balance. You are rewarded for fitting the data, but you're penalized for making your transformation too extreme or complex.
Exactly. It beautifully balances the reconstruction error against the complexity of the transformation.
Now, there's a really important detail tucked away in the appendix that I think is crucial for anyone who actually tries to implement this. We keep talking about invertibility, not breaking the clay.
Right.
But mathematically, if I just let a neural network pick random numbers for the parameters of the flow, couldn't it accidentally pick numbers that break the math, that make the function non-invertible?
It absolutely could, and it would. For the planar flow, for example, they use a $10 nonlinearity. And for that function to remain invertible, to prevent it from folding over on itself, the parameters have to satisfy a specific condition, $10 $9 1.
And if that condition is violated during training?
Your function becomes non-invertible. The Jacobian determinant hits 0. The log of 0 is negative infinity. Your loss function explodes, and your training run crashes and burns.
So how do they stop that from happening?
They use a really clever numerical trick. Instead of letting the optimizer directly tune the parameter dollar, they optimize a different unconstrained parameter, let's call it had to, and then they run that through a special function that forces the resulting dollar to always satisfy the invertibility condition.
It's like putting bumpers on the bowling lanes. The network can throw the ball however it wants, but the math guarantees it always stays in the lane and never goes in the gutter.
Exactly. And that's the kind of detail that distinguishes a purely theoretical paper from a truly practical engineering paper. Razende and Mahamed anticipated the implementation headaches, and they solved them for you.
Okay, so we've covered the finite flows, these discrete steps, but then the paper takes this turn into the deep end of the theoretical pool. The authors ask, what happens if the number of steps, $os, goes to infinity?
This is, for me, the most profound theoretical section of the entire paper. This is the concept of the infinitesimal flow.
Right. When you take a sequence of discrete steps and you make them smaller and smaller and more frequent, you leave the world of algebra and you enter the world of calculus.
You get differential equations.
The sequence of maps becomes a continuous time evolution, a partial differential equation describing how the probability density just flows over time.
Correct. And they make this incredible connection to a very famous equation from statistical physics, the Langevin equation.
The Langevin stochastic differential equation, or SDE, what does that describe?
It's used to describe the motion of particles suspended in a fluid, what we call Brownian motion. The particles are being pushed around by some force, like a gradient, but they're also being constantly kicked around by random noise from the fluid molecules.
Okay, but why does a paper on machine learning care about dust motes floating in a fluid?
Because of where the dust settles. If you run a Langevin process for long enough, the distribution of all the particles settles into a stationary state. It stops changing. And that stationary state is called the Boltzmann distribution.
And the Boltzmann distribution is what in our context?
It's proportional to the power of negative energy. And in our machine learning context, the energy corresponds to the error of our model. This means that the stationary distribution of the Langevin flow is the true posterior distribution we were trying to find all along.
Hold on, let me just restate that to make sure I'm getting the full gravity of it. Are they saying that if your flow is long enough, infinitely long, then variational inference is no longer an approximation, it becomes exact?
That is the theoretical mic drop of this paper. Yes. It fundamentally bridges the philosophical divide that existed for years between variational inference and MCMC.
Because traditionally, Villestives was always seen as biased but fast, and MCMC was seen as unbiased but slow. They were two totally different schools of thought.
Exactly. But this paper argues that they're really just two ends of the same spectrum. MCMC methods like Langevin Monte Carlo are effectively a flow with infinite steps. Standard 6 is a flow with a small, finite number of steps.
So the variation gap isn't some inherent, unavoidable flaw of the method. It's just a limitation of your computational budget.
That's it. If you can afford a longer flow, you close the gap. It's an engineering problem, not a fundamental theoretical barrier.
That's a huge unifying theory. It connects everything. VI, MCMC, they even mention Hamiltonian Monte Carlo, all under this one conceptual roof of flows.
It does. They explicitly show how Hamiltonian Monte Carlo can be viewed as a volume-preserving flow on an augmented space, a space of position and momentum. It really cleaned up the entire theoretical landscape of approximate inference.
Okay, before we look at the experimental results, we have to mention the rival, the other flow paper that came out at the same time.
Ah, yes. Nice.
Nice. Nonlinear independent components estimation by Din, Kruger, and Bengio. It's funny how that happens in science, this multiple simultaneous discovery. But NICE had a slightly different philosophy.
It did. NICE focused exclusively on volume-preserving flows. They designed their architecture in a really clever way so that the Jacobian determinant is always exactly equal to 1.
Which is very convenient for the math. The log of 1 is just 0, so that whole extra term in the loss function just disappears.
It makes the math super simple. But Razende and Mahamed in this paper offer a subtle critique of that approach. They argue that forcing your flow to be volume-preserving is actually too restrictive.
Why would that be a problem?
Okay, think about packing a suitcase. If you're forced to preserve volume, you can rearrange the clothes inside, but you can't squish them down.
Right.
Now imagine your posterior distribution is a tiny, sharp, peak-like, one very specific solution to a problem, and you start with a big, broad Gaussian. A volume-preserving flow has to stretch all the empty space around that peak infinitely thin to compensate for compressing the probability into that one spot. It's very inefficient.
So NUS is like packing a suitcase without being allowed to sit on it to close it. Normalizing flows lets you sit on the suitcase.
It is a perfect analogy. By allowing the determinant to be non-one, by allowing for expansion and contraction, Razende and Mahamed's flows can match the scale of the true posterior much more easily and efficiently.
All right, let's see if sitting on the suitcase actually worked. Let's get to the results. They start with this really compelling visual proof in figures 1 and 3 of the paper.
These figures have become iconic in the field. They're in, like, every deep learning lecture on this topic. They created these nasty 2D synthetic data sets specifically to torture the models.
Can you describe them for us?
Yeah, one of them looks like a boomerang. Another one looks like a wobbly snake or a sine wave. And one is particularly mean. It's two completely separate blobs of probability, like two islands in an ocean of zero probability.
And first they tried to fit these shapes with the standard mean field Gaussian, the old square wheels approach.
And it failed miserably, as you'd expect. For the boomerang, the Gaussian just sat in the middle, covering the empty space between the two arms. It captured the average location, but absolutely none of the shape.
And for the two islands, what did it do there?
It just drew one big circle around both of them, covering the entire ocean in between. It was a terrible, low-fidelity approximation.
Okay, then they turned on the flow.
And it's amazing to watch through the figures. With just k-key-22 steps of a planar flow, you can see the initial Gaussians start to twist and stretch. It's no longer a simple circle.
And as they add more steps,
By the time they get to T3326, it's almost perfect. The distribution has wrapped itself perfectly around the boomerang. It snakes its way through the wobbly wave. It's incredible.
But wait, what about the two islands? I thought we said you can't break the clay. How did it model two completely separate blobs?
Ah, that's a clever observation. You're right, it can't break the clay. The distribution has to remain a single connected component. But what it can do is stretch the connection between the two blobs until it is infinitely thin.
Like a filament.
Exactly. It creates this thread of probability connecting the two islands that is so thin and has so little mass that it's practically zero. So visually, and for all practical purposes, it looks like it has successfully split the mode and captured the multimodal structure.
That's really impressive. But 2D toy problems are one thing. Did it actually work on real high-dimensional data? MSIFAR 10.
It did. They trained a deep latent Gaussian model, which is essentially a VAE, but they replaced the simple Gaussian posterior with one of these flow-based posteriors.
And they measured the negative log likelihood and the bound.
Right. Lower NLL is better. A higher, tighter bound is better.
And what did they find?
A very clear, systematic improvement. As they increased the flow length, dollars from dollars, which is just a standard VAE to 10, then 20, then up to 80, the error just kept dropping and the bound kept getting tighter.
So it wasn't just random noise, it was a definite trend.
No, it was a very clear monotonic trend. More flow equals better inference. On MNIST, they significantly outperformed the standard VAE, and they also beat the nice model we mentioned earlier.
What about the computational cost? Did adding 80 layers of flow just kill the training speed?
And that's the kicker. Because of the linear time complexity of the determinant calculation, the overhead was minimal. Most of the heavy lifting in a VAE is done by the convolutional networks in the encoder and decoder that are processing the images. The flow is just a little bit of extra math happening on the small latent vector, so you get this massive boost in expressivity for a very, very small price in terms of wall clock time.
Talk about amortized. The benefit is amortized over the whole training run.
That's a good way to put it.
So looking back now from our vantage point here in the present day, what do you see as the lasting legacy of this paper?
I mean, it really kickstarted the flow boom in probabilistic machine learning. After this paper came out and showed that the Jacobian bottleneck was solvable, the floodgates opened.
We got a whole zoo of new flow architecture.
A whole zoo. We got masked autoregressive flows, or MAF, inverse autoregressive flows, IAF, real MVP, GLOW. The list goes on.
GLOW was the one that gave us those really famous demos of generating celebrity faces, right? Where you could slide a bar and make a face smile or get older.
Yes. That was a direct descendant of this work, just using a much more powerful and expressive flow architecture.
So it laid the foundation for modern generative modeling.
Absolutely. And even today, if you look at diffusion models, the engines behind DALL-E, Midjourney, stable diffusion mathematically, a diffusion model is a hierarchical latent variable model that transforms noise into data over many, many small steps.
It sounds a lot like a flow.
It's a different mechanism. It's stochastic instead of deterministic, but the core philosophy, transforming a simple distribution into a complex one through a sequence of reversible steps, that DNA comes directly from this 2015 paper.
It really cemented the idea that inference itself is just another thing we can learn with a neural network. It's not a fixed equation. It's a flexible, trainable process.
And that if you have enough layers, if your flow is deep enough, you can turn a simple blob of noise into a masterpiece.
Which is a beautiful thought. Okay, we've done the history, we've done the math, we've done the results. Now it's time to get a little bit speculative.
My favorite part. I'm ready.
It is time for our novel notions segment.
Yes. Let's do it.
Okay, standard disclaimer for everyone listening. The following segment involves speculative ideas based on the paper's logic. These are unchecked, peer review pending hallucinations. This is for entertainment purposes only.
And if you do write a paper based on this, please put us in the acknowledgement section.
Notion number 1, the psychological flow, or what I'm calling the cognitive bounded rationality model.
Okay, I'm intrigued. Lay it on me.
So the paper clearly establishes that the complexity of the distribution you can model is determined by the flow length, collars, If SK dollars, you're a mean field thinker. You assume everything is independent, fire is hot, ice is cold, simple, uncorrelated facts.
Right. Your world model is very simple.
But if you have a flow with K100 dollars, you start to see the correlations, the nuance. Fire is hot, unless it's a cold plasma, or unless I'm wearing a state-of-the-art heat shield. You are refining your posterior belief.
Okay, I see where you're going with this.
Exactly. Now, the field of behavioral economics, guys like Kahneman and Tversky, tells us humans are boundedly rational. We use heuristics, we make systematic mistakes. Why? I propose it's because our biological inference network, our brain, has a dynamic constraint on dollars.
So you're saying that panic is just the brain setting K-O-yan.
Yes. That's it, exactly. When you're in a high-stress fight or flight situation, your brain has to make a decision now. It slashes the flow length to save time. It performs a single planar cut, friend or foe, run or fight.
It ignores all the nuance because calculating the Jacobian for 50 steps takes too long, and the lion's going to eat you.
Precisely. That actually makes a lot of geometric sense. You could model cognitive biases not as errors in thinking, but as optimal variational inference with a truncated flow.
Right. We aren't irrational. We are just optimizing for latency. We are performing low-fidelity inference because we're running on limited hardware with a strict time budget.
And wisdom or expertise could be modeled as just having a really well-trained, efficient flow. An expert can reach a complex, accurate posterior in cable 5/0 steps, whereas a novice needs K5 dollars and just runs out of time or cognitive energy.
I love that. It reframes psychology as a geometry and optimization problem.
It does. It's compelling.
It really is. Okay, what's notion number 2?
Notion number 2, this one is for the hardware geeks out there. I'm calling it thermodynamic flow control.
Okay, so you're connecting this back to the Langevin flow and the Boltzmann distribution we talked about earlier.
Exactly. The Langevin flow settles to the Boltzmann distribution, which is defined by energy and temperature. Now, in the math of the paper, temperature is just a noise parameter you can tune. But in a real-world data center, temperature is a very real, very physical problem.
It's the limiting factor for performance. Chips melt. You have to throttle them.
Right. Right now, we treat heat as a waste byproduct of computation. What if we use the flow architecture itself to actively control the physical heat on the chip?
I'm not sure I follow. Explain.
Well, we usually optimize the parameters of the flow to make the model's output distribution match the data distribution. What if we added another term to the loss function that penalizes hotspots on the silicon die?
So you are coupling the statistical distribution of the software directly to the thermal distribution of the physical hardware.
Yes, thermal variational inference. You would have a differentiable model of the chip's thermal physics. The flow would then be forced to learn to distribute the probability density, which correlates to transistor switching activity and thus heat, in a way that perfectly matches the cooling capacity of the chip.
So you're using the math of the flow to dynamically route the computation around the hot parts of the chip.
Exactly. The software literally flows around hotspots like a liquid coolant. If a core gets too hot, the Jacobian determinant of the flow shifts to compress activity away from that core and expand it into a cooler region of the silicon.
That is wild. You'd need an incredibly accurate and fast thermal model of the chip inside your training loop. But if you could do that, you could essentially run chips at their absolute maximum thermal limit 100% of the time without ever throttling.
Self-cooling algorithms.
You're connecting the information entropy of the model directly to the thermodynamic entropy of the hardware. That's a deep connection.
NVIDIA, if you're listening, I accept payment in H100s.
We'll see. We'll see if they call.
Okay, to wrap this all up, Variational Inference with Normalizing Flows. It's a dense paper. It's a math-heavy paper. But at its core, it's really a paper about freedom.
Freedom from the tyranny of the Gaussian.
Freedom from the Gaussian. Razende and Mahamed showed us that if the world we're trying to model is complex, we don't need to dumb down our models to fit our math. We just need to give our models the flexibility to flow.
And that single insight is still powering so much of the generative AI revolution that we are all living through right now.
If you want to dive deeper into the math, we've linked the paper in the description. And I'm serious, the appendix is a goldmine of practical tricks.
Definitely read the appendix. It's where the real engineering is.
Thanks for listening to Talk Tensors.
Keep learning.
We'll see you on the next deep dive.